Hi. So my name is Bertel Schjerning. I'm from University of Copenhagen. It's on, right?
Okay,
yeah, I think it's on. And I do dynamic structural econometrics, and I'm going to take you all the way back to the 80s, okay, 1987. And there's something called Rust 1987. I'm not talking about Matthias Rust, who actually landed the Red Square that year, but it's John's paper. And it's all about this guy. So I'm going to talk about two things first. I'm going to talk about the nested fixed point algorithm, the algorithm and method to estimate dynamic discrete choice models by maximum likelihood that John introduced and used in that paper, Rust 1987. And a pretty peculiar title, pretty cool title. It's called Optimal Replacement of GMC Bus Engines, a Empirical Model of Carroll Circuit. It's actually exactly what it is. It's a model of this guy, okay? And how he replaced engines in this bus fleet. He would be like the superintendent of maintenance every month, coming buses in, and he'll look at the mileage. Okay, now we can go a little bit further. Or he thought, oh man, I better replace that engine. And so it's like an optimal stopping problem, discrete choice model. So that's what we're gonna try to model. Now, John did an infinite horizon model, but the guy, he had almost infinite horizon. He was like monthly choices, and he lived until the age of 94. But you know, not all models are perfect. Actually, I've learned that something called Sturctual gesaltishness, which is like a very delicious dish. You get it in Zurich. So I think it means that you're like from Zurich. Sturctual, yeah. I'm not sure.
But I think that John, I don't know, but John told me once that he bumped into the guy from Lausanne.
That's exactly right. I'm not going to leave more details there, but he got the data, and he also says now he's not here to tell stories, right? But he says he literally got his hands dirty with the data because of like grease and oil over all these books that Harold Zucker wrote down the odometer readings. So he really got to like get his hands dirty with the data. Anyway, what is this paper about? It's like a path-breaking paper, right? It introduces this methodology to estimate single agent dynamic discrete choice model. I mean, lots of people have probably heard about Harold Zucker already, right? But I think it's a very good starting point for talking about structural estimation of discrete choice models. It's a place I started at least. So what does it give? It has this nice illustrative application of a simple model of optimal replacement. In fact, John, when he submitted this paper to Econometric many years ago, Angus Deaton, who was the editor at the time, he said, you know, all this nested fixed point algorithm looks pretty cool. Show me the actual works in practice. And then he went out and searched for Harold Zucker and revised the paper, included the empirical application, and he got the paper published. So it introduces this nested fixed point algorithm. You heard about fixed point algorithms right now, right? So now it's just nested inside an estimation routine because we want to learn the deep structural parameters of Harold Zucker's cost functions. Okay, so what we do is we search over the parameter space. Okay, and then there's an inner loop that solves the fixed point problem. That inner loop is nested in that hill climbing algorithm that try to maximize the likelihood function. So that's really what it is. Okay, now these models suffer for all sorts of issues, computational daunting tasks. And so what John did was he formulated a nice set of assumptions that made these models tractable at the time. And I'm going to go review some of them. And many people use them, still use them, or like deviate like a little bit. And then he's like the first guy to say maximum likelihood estimates of dynamic discrete choice models. And then once you've done, he used this model to kind of micro aggregate from Harold Zucker's decisions the demand for engines. And then you kind of change the parameters of the cost function, which is like the price new engines enters. And then you got like a demand curve. It's like micro founded demand from a structural mode. Okay, so that's what we're going to try to do. And you may say, who cares about heteroscopy? Okay, so lots of people do. And in fact, I mean, here's just a long list of applications in this or related paper: occupational choice, retirement, brain choice and advertising, choice of college major, all these discrete choice models out there where people make choices today that affect the future possibilities or future states, or future potential. Okay, so this is like a long list, and I'm going to go not through the list today. We want to go home, right? Take some rest. At some point, I'm going to try to do Harold-Sucker later together with Feder. You call it Harold-Sucker and steroids. It's just like it's not engine replacement, but it's like car replacement, and this equilibrium component kind of bridges to some of the next topics. It's about the equilibrium trade in the automobile markets. We don't choose just whether or not to replace the engine, but choose when you replace, what car do you want to have, what type, what age, and you can buy used cars and sell your used cars and so on. So we'll get to that later. Okay, now there's several other ways to estimate this. I'll talk about that in a second. Here's the Big Mac index, dynamic structural econometrics. This is the citation curve of Rust 9087, and it's still going up. Okay, we have rejected the exponential, but this is the change every year is still increasing linearly. Look at the R squared. It actually used to be 0.999, which is like what John assumed is discount factor for Harold-Sucker. So, but it's not completely tiny. Anyway, it's still, people are still using this, and I would also consider, like, for me, I'm an old fart, like the NFXP is like my Swiss Army knife for structural estimation. It's like a very good starting. Okay, we're going to talk about today also another way to do it with mathematical programming with equilibrium constraints by Sue and Judd. Bob Miller is going to talk about CCP estimation. So, but there's many other ways to do this. So let's just get to it. I think one thing from reading all these different papers, just realizes that at least those that have to do with discrete choice models, you kind of have to confront Harold-Sucker. So if you come up with a new algorithm, well, you use John's data set, and then you try it. If you can't do that, well, then maybe you should revise your algorithm. Okay, let's go to just review some of the primitives of components of dynamic models. So we have decision variables. That's like the vector of variables that describe what the agents are doing. This is what John called the action, right? So, and there's a choice set. Decisions lives in a choice set that can be state dependent. Okay, and we can assume D is discrete. So 1, 2, 3, 4, 5. In the Harold-Sucker, it's 0, 1. Replace or not the engine. And the choice set, well, that could be state dependent. Some years, some ages, if you're thinking about a model of contraceptive choices and you already got sterilized, you can't have more children. So it's clearly like a state-dependent choice set. Okay? But here it's just 0, 1 every time, every period. Got the state variables. We're going to call those F's, S, and they describe all the relevant information about the model decision process. So we know about that. Then we need the payoff function. I'm going to call that U. That's what with the rewards before. So the state and decision specific utility you get in the current period, and we're going to assume time separable utility. And then we're going to look at motion rule. The motion rules. That's the last thing we specify. That's the conditional density of the state transition. So you wake up in the morning. You're in state S. You do D, right? That makes you take a decision, and tomorrow you're in a new state. Like if you have a bus of 100,000 miles, you replace the engine. Tomorrow it has 0 miles, plus potentially how much it was stochastically driving during the period. So that's a state the state transition, and we're going to assume that the agents are rational in the sense that their beliefs are in line with with the way these states are developed. Okay, the solution, well, can take many forms, but it could be the value function, which is like the maximum obtainable utility at any state, or the policy function that gets the mapping from the state space to the action space. So that's in some sense we already talked about all this. Now what I wanted to talk about now is how do you estimate this model? Okay? So what we're going to do is we're going to parameterize the utility function. It's going to be parameters theta u for those that enter into utility function. These are like the parameters of Harris-Zucker's cost function. Okay? Let's say. And then there's going to be parameters that index the motion rules for the states or the state transition. We're going to call those theta p. And there could also be parameters and indexes choice set. If you have a model where the liquidity constraints, and we parameterize how banks are doing. Okay, now we need a parametric model. Once we have a parametric model, we can solve it by dynamic programming, right? It gives predictions, and then those predictions we confront with the data, and then we search for the parameters so that the model fits the targeted data. Okay? This could be like various aspects of the, you can't see it, but I can. Aspects of the data, which is like a subset of decision states and payoffs and so on. I should probably, what can I do to make this disappear?
I couldn't.
I can't. Okay, well, we'll just have to live with that. Okay, so back to Harris-Zucker. Here's the choice set for Harris-Zucker. It's 0 or 1, right? Engine replacement D equal to 1, ordinary maintenance, no replacement, D equal to 0. Harris-Zucker, he has two subsets of state variables. Here's something that we as econometricians observe. It's called X, which is the mileage since last engine replacement. This is what Harris-Zucker would write down in the books, and John would type it. The data set is by the way, it's on GitHub. You can, the code and everything, you can replicate these results. Anyway, this is an observed state variable. Then there's the unobserved state variables like a taste shifter. And these are, from our perspective, completely random. We don't know what they are. Can't observe that. But Harris-Zucker, he looks at the epsilon and says, oh man, there's smoke coming out of the pipes. So maybe there's a big epsilon for replacement. They're going to be decision specific, one for each alternative. Okay, here's the utility function. So let's start with what happens if he's not replacing. Well, he's going to get, we'll have to pay the cost, the maintenance cost, we call that C. Parameterize that by theta 1. Okay, sorry, I called theta u before, but now the theta 1. Okay, and then this RC, that's another parameter. That's a replacement cost you pay in case you replace the engine if D is equal to 1. Okay, and then you pay the maintenance cost of a brand new bus because now you just replace the engine. Beyond that is these additively separable taste shocks. This is your total function. Okay. We can assume the epsilons are IAD with this conditional density Q. Okay. We can assume that the mileage since last replacement is following what John terms the regenerative random walk. Okay. So it's like you replace the engine, it goes to 0 plus some driving, okay, plus some noise. It's like a random walk, okay? But you can replace it and then put it back to 0. And then what we want to estimate is these parameters. It's RC, it's the replacement cost, it's a parameters cost function, and the parameters of the state transition process, these parameters here. Okay. And then what I've hidden here below is those parameters we're not trying to estimate. Okay, so we're not trying to estimate beta, we're not trying to estimate the parameters here in the distribution of those epsilons. In fact, we're just going to assume they are at extreme value, and you have usual issues with scale normalization, level normalizations you have to do in discrete choice models. In the end, once you have that distribution pinned down, there's no parameters for it. So I'm just gonna leave it at that. Okay, so here a sucker, he's maximizing, he's taking the sequence of actions to maximize the expected discounted utility over the infinite horizon. And I'm just going to jump right through the Bellman equation. It's an equation that kind of that represents that in infinite horizon maximization problem. Okay. So then by Bellman's principle of optimality, then the value function constitutes a solution to this Bellman equation we've just seen. Okay, now this is, it's a simple model, but if you look at it more generally, it's potentially it could be hard to compute. There's several things to think about, right? X is continuous, right? There's only one X, but what are the several explanatory variables, several state variables? Epsilon is continuous, and if there's like a J discrete choices, it's like you're carrying around a J-dimensional state variable. Because the value function is a function of the state variable. So in principle, you need to be able to solve this in all the different combinations of the state space in order to be sure you have like full solution. So this is very high dimensional, right? And evaluating also this expectation here, this is the expected future value. Well, you need to calculate, deal with these integrals, right? This was only a one-dimensional integral. You have one state variable. This is potentially a high-dimensional integral. If you have many state variables that are observed, well, it's generally just a big integral. But you can break that cursor dimensionality using Monte Carlo or something. You will still have to evaluate that function inside, that high-dimensional function. That's maybe where the neural nets come. I'm sure Simon will tell us all about that. Okay, so what's else on this list? Well, it's non-differentiable because of this hard math operator. So what can we do? What did you do in 87? Well, made assumptions. Okay, first of all, it's going to assume the utility function is additively separable in these two sets of state variables. Okay, so these epsilons are just some errors that are added at the end and makes it these two properties. Then he introduced something called the conditional independence assumption, stating that the state variables S, that includes both X and epsilons, is this conditional independence control macro process with this probability density. Okay, so here you got, this is really ST plus 1, and this is ST, this is the decisions. Okay, but it factors into this way. Okay. So what you should see is once you've conditioned on the xt plus 1, well, the epsilons doesn't depend on any past epsilons, for example. So all the dependents go through this observed state transition, which you can estimate from the data, because X is observed and D is observed. What does it rule out? For example, serially correlated unobserved state variables. They will clearly depend on the previous state. So you can't have that. You could still extend the model, right? And then you say, okay, maybe there's another state variable that is serially correlated, but then conditional on that, it's conditional independent. It's what people do. Okay, so we're going to make use of another frequently used assumption. We're going to assume that these epsilons are in fact either extreme value distributed. So it has this nice CDF. And what it gives us is closed form solutions for choice probabilities and the expectation of the max. I'm going to show you that in a second. They're going to be logit and log sums. Okay, so here we got it. Actually, we already simplified a little bit because here I've already utilized the additive separability assumption and put in the state transition that obeys the conditional independence assumption. It factors in this to this P and Q. Okay, so what we can do is we just quickly go through and see how these assumptions, the additive separability, it should be AS. And conditional independence allows us to separate out the deterministic part from the choice-specific value functions. And then that how the conditional independence assumption allows us to work with this problem on a much reduced state space. Okay, now the state space originally was spanned over both epsilon and eps, but magically we can get those epsilons away. And then finally, we can compute the expectation of the max using the properties of the expected value function, the expected value function, the extreme value type 1 distribution. We also get like nice conditional choice problems. Okay, so let's just one by one. That was math. Okay, so first, here's just essentially rewritten what we had before. And what you see here is that what this allows us is that we can separate out this what we'll call this deterministic part of the utility function, okay, or the value function. That's the sum of the utility function and beta times the expected value function conditional on the current state and decision. Okay, and then you have the epsilon out there. Everything that's here is really just this first part. This means we can just use the machinery of standard random utility models. Okay, so it looks like that. So here, once this epsilon here becomes I at extreme value, well, taking the expected value of that max in closed form with respect to that epsilon is just becoming a log. So calculating the argument that maximizes that solution. Okay. Now we can also express the value function over the entire state space. That works with the value function, works with the expected value function. So essentially, we're just integrating over the next period states to define this conditional expectation of the value function. Call that the EV here. And then because of the conditional independence assumption, we can express it. We can express the value function or the Bellman equation on expected value function space. But see, if you look at what is in here, well, you got the value function here, right? And that has the expected value function over here. So essentially, you got a mapping from expected value functions to expected value functions. And what John shows is that this operator here, that mapping from expected values to expected values, is a contraction and has a unique fixed point on that operator. Okay. Why do I want to do that? Well, it's good with contractions, right? Because we got global convergence of VFI, value function iteration. We just talked about that. But in this expected value function, we integrated out those epsilons, right? So it's much lower dimensional, so you would never have to store all those epsilons on your computer. Or store the value function for all these different combinations of epsilons. So that's makes this problem much lower dimensional. You could alternatively, you could integrate not over both state variables, but just over the epsilons to get rid of those. So people call that the integrated value function. We call that B little bar. So this has a similar flavor. Again, you get like a mapping from this integrated value function to integrated value function. The Bellman equation is not just expressed in terms of the integrated value function, where we just integrated out those epsilons. Okay. And this is even lower dimensional, it doesn't even depend on the decisions. So we eliminated one problem here by assuming conditional independence. It's this dimensionality of this expected value. Okay, then we still need to compute that expectation of the max, this guy here, expressed in terms of that integrated value of the expectation of the max of these choice-specific, the deterministic component of the choice-specific value functions plus those epsilons. Take that expectations with respect to the epsilons, and then the max over all these different choice alternatives. Replace or not replace. What is that? So that's a log sum. What is the argument to maximize what is the smooth argument? That's a choice probability. It's the expectation that D, the choice under consideration, was in fact the argument that maximizes the choice-specific values, including those epsilons. We can calculate that probability because taking expectations of indicator functions of functions that we know plus I at extreme value errors, they're just logit formulas. Right? So we are left with something that's just much easier to compute, right? Think about the alternative. You want to take that expectation, you need to take an integral over all those all those epsilon shocks, evaluate that that indicator function, and count how many people choose replace and how many people choose keep the slightly accept reject. Okay, so huge benefits. Once J-dimensional integration over the epsilons. And then on top of that, the things that turns out to matter when we want to estimate this model that you can't see, but I'll tell you, the conditional choice probables, this guy, the integrated value functions or the expected value functions. These are all smooth functions now, okay? They're differentiable. You can change parameters that change smoothly. Okay, if you try to estimate models, you like to use gradient-based maximization routines and try to see if you can calculate derivatives of the likelihood function. But what you're trying to differentiate is not changing, because it's a step function or it's kinks and stuff, then things becomes all the more difficult. So these are nice assumptions, but you can still relax your model within that. Keep that maybe a little bit of epsilon shock, and you do like a logit smooth, accept reject simulator of some other structural model you have in mind. And they will still be smooth. So I like logit. Okay, so let's put this together. Now we want to do maximum likelihood for discrete choice models. In order to do that, we need the choice probabilities, they enter into the likelihood. You see here, those choice probabilities, they depend on the expected value function. And in order to compute that, well, you need to compute the fixed point on the Bellman operator, right? So you see here, as you would search for, to maximize the likelihood function that depends on these choice probabilities, you would need to solve this equation every time to change the parameters. A key thing here is that it's important this is a contraction, because if it's a contraction and this equation on the right-hand side is indexed by those parameters, then this unique fixed point is also changing smoothly with those parameters. It's like an implicit function of those parameters. Okay, so we have then used this theta to emphasize the Bellman operator here really depends on the parameters. I mean, clearly, right? You change utility function parameters, you get a new right-hand side, right? So it does depend on the parameters. Same thing with the transition probability. The parameters that affect the transition probabilities affect that expectation calculation. They're entering in here. And then also the expected value function and the CCPs, those conditional choice probabilities also up here, depends on the structural parameters. Okay, now we're not going to do neural nets or Chebyshev polynomials or anything. We're just going to do like John did. Discretize a minus state space. It's continuous variable. And just jump it into the 90 bits or 175 bits. And then we're going to formulate finite state macro transition matrix for each of the two choices, keep or replace. And they look something like this. Okay, so this is where you wake up in the morning, you have, say, mileage, brand new engine, and then, I'll say maybe the last interval, probably something like 450,000 miles, okay, ready to go. And then these are the probabilities of changing to the next bin tomorrow. So this is going to be probably you stay in the same state, probably you move up one, probably you move up one further. At some point, the probability is zero. Because you have a brand new bus, but it's not very likely that you go 450,000 miles within 1 month, right? So that's why some of these probabilities are just put to zero. We can estimate this from the data. Whether you can parameterize and estimate on underlying parameters. Now this is what happens if you're keeping the engine. Another thing to notice here is got zeros down here. Any ideas why you got zeros under the diagonal?
You can't reduce the mileage.
One more time.
You can't reduce the mileage.
You can't. You're not driving backwards, right? Exactly. Right? You can't reduce the mileage. It's not like you put the bus on the road and then it comes back brand new. You have to do something. What you can do is you can replace the engine. That reduces the mileage to zero, and then it's going to stochastically drive within the month. So we end up with a state transition, something like this. Okay. This we can also write in matrix form. Okay, so it's easy to do injects. Okay. Or in MATLAB that I'm going to show you in a second. Okay, so here's just a little, also makes the differences between these two ways of expressing the dominant equation a little bit more clear. It's really about the location of these state transition matrices. So you've got the state transition here. That's like the integral over the future states conditional on the decisions. Okay, so this guy here, that's conditional on the decision. Okay. Then multiplied by the integrated element, or the log sum. Okay. And here clearly you can see this is a mapping from the expected value function to the expected value function. You could do successive approximations and you got your EV. If you do with the integrated value function, well, then what you put in is the integrated value function. To get this to the expected value function, you do the integral over the Myers process, or not the integral. You multiply with the state transition matrix conditional on that choice D here that you're summing over. And then you get your new expected value function after you throw it through the log sum. So, same thing again. Okay, now we're going to estimate. We're going to assume that with data on replacement decisions D and mileage. Easy thing to say is we just have panel data on both, but really you don't need both of it. You need transitions on the states together with the decision variable. So it could be that you have mileage today plus, monthly mileage plus the decision, or you have mileage today and tomorrow and then decision. You don't have to have a whole sequence. But this is enough for us. So we're going to take those data and then we're going to form a likelihood for that our model can predict that. Okay, so there's two components, right? There's the log of the likelihood for the state transition. Notice here we have a model. Okay, it's just a parameterized model. No dynamic programming or anything is required. Okay, and it doesn't depend on any other parameters than what I call theta 3, which is going to be, to confuse you totally, these parameters in here that are now called pi, okay? Okay, so these are the parameters of the state transition. You can estimate that in the first step, just from the transition and data. But then there's this guy here, we already talked about it, that's a conditional choice problem, so in turn depends on the expected value function, which we need to solve doing dynamic programming. Yes?
What's the difference between those two terms there in the little L of F line, second line, that term and that term?
That term?
Yeah.
And that term. Oh,
No, that term and then the term to the right of it.
okay, that.
This?
This?
Yeah, this versus that.
And
yeah.
this, okay. This is the probability for choosing D, or the observed DIT, given the current state. This is this choice probability. Okay, this is what we have down here. It's just written, not evaluated at the particular choices. We throw in the data, evaluate the choice probabilities for those observed choices, given those observed states, using this formula. Now, this other thing here, well, that's just the, if you have, you have a likelihood for that part, for this state transition, how the mileage is changing over time. Okay, this is for, to predict observed mileage. This is to observe the conditional on previous mileage. This is to predict the observed discrete choices. So it's just two different variables, like the contribution. What I was trying to say before is that for the latter part, this last part, you don't need to solve a model. We just have a parametric model for how those states are evolving over time. That's this part down here. It's this part down here. Okay, that we now discretize. So it's the parameters into these state transition matrices. The pies.
What is I?
I, that's the index of the observational unit for buses. Okay, bus 1, 2, 3, 4, 5 up to M. T is time. You observe them over time. Okay, so that's what we're going to do. In a more abbreviated version of this, it is like this: the nested fixed point algorithm to solve the unconstrained optimization problem, where like this, you search over the parameters to maximize that likelihood function, taking into account of the expected value functions that enter into the likelihood function through those choice probabilities. Right in there. If those are changing every time you change the parameters, you need to solve a new problem. So how do you do that? Well, you search over the parameter space, maximize that likelihood function. Here you could use your gradient-based solver now, right? Because this is a smooth function, because the CCPs and the expected value functions, everything here, including the likelihood, which is just an aggregation of that, is now a smooth function of the parameters. And to our discussion before about what is the required tolerances. Now here you really want to solve that tightly, right? Because especially if you're using numerical gradients, you make a tiny change to the parameter, calculate that numerical gradient, and then the tolerance of that inner loop that solves that equation is not tight enough, then maybe you just end with the same thing you've thrown in to begin with, and derivatives are equal to 0, or you get another step and get a big approximation out. This is where you want to have it like at machine precision, something like 10 to the power of minus 14 or something. Okay. So how do you do that in a fixed point? Well, we know about the successive approximations. We know about Newton or Howard. Okay, I'm going to just call it Newton. And we're going to do both. We're going to start with successive approximations, and then we're going to do Newton's method. See, the benefit of Newton's method is it's quadratic convergence. You'll see that in a little bit. That's okay. So, well, I did say he got his hands dirty with the data. What is the data? He got his maintenance record of these 162 buses. Monthly observations of mileage of each bus, the odometer reading, and then he had data on these replacement decisions. Essentially, what we assume so far we could observe. And here's the data. It's not this little guy here that jumps forth and back. That's a non-parametric hazard. he's dividing here the data just into like something like 100 bins, and it's just counting how many replacements was there at each bin. And you can see it's happening a little bit more frequently as those buses they go. Okay, now when I have some smoothing and a model that just doesn't make this jump around all the time. So he has two models. Here's a dynamic model. This is a prediction from the dynamic model, and then there's a prediction from a static logic model. And then you do this. Here, the parameter estimates. It's just taken from the paper. And we could try to see if we could replicate some numbers like this. Okay, so what is he estimating? Just like I said, replacement cost, the parameters of this linear cost function, this parameter here, this is the parameter we're estimating. Okay, and then theta 3, that's the transition parameters, those parameters that were in the state transition matrices. Okay, so with probability 34, you're going to stay in the same state at this level of discretization. Okay, so how many grid points did he use here? 90. Okay, because this number changes, you change the grid point dimension. Okay, so here it's 175 grid points, and then drops to 0.10. And we're just going to try to see if we can approximate or estimate that distribution. And then with probability 0.5, you go to the next, and then you go to the next. And then after that, there's 0. Again, here the replacement cost is a cost parameter. You compare it to the static model, you see here the replacement cost is just much smaller compared to the dynamic model. It's not so surprising, right? You need to rationalize why this dynamic forward-looking guy is replacing his engines after all, right? You just observe his replacement. You want to learn from these data. Why is it replacing? Well, it must have been because those replacement costs were low relative to how the operating cost would be in this existing fleet. Okay, so why don't we try to see if we can do this? Now in the repo, there's something here. It's in MATLAB and there's in Python. Okay, I'm going to do MATLAB, and you can do Python. The MATLAB is well, that's what you're going to see in a second. We have no chance we can just go into details with the code anyway. But there is actually some Python Jupyter notebooks, and you can try to see if you can replicate this both with various different methods, with mathematical programming with like equilibrium constraints MemPeg, with this NFXP, and with the nested pseudo likelihood and CCP estimators. I think that's the problem sets there are. And you're lucky, Jakob is here to answer all the questions. He's the TA in my course. Okay. So sorry for putting you on the spot. Anyway, maybe you can figure it out yourself, but it's structured in this way. There's two types of code, there's X and a code. Start with that. That's where it's with any intellectual consensus that says fill in. And if you can't do that, well, you go to the X post and see the answer. Okay, but okay, we're not going to do exercises now. We're just going to try to see if we can illustrate this code here. I'm going to just try to run some code, and this I'll be using this, and there's a little README file that says what all the different files are doing. Okay, so that's what's on GitHub. I'm going to just completely switch from that to my terminal and my old, previously favorite editor, text. I'm doing years ago. Okay, so what I want to do is just to run and see if it works. It's called run bus data, and you can go in and modify and it does work. And it does also run pretty fast. Okay, so 0.24 seconds or 24 seconds to estimate this on a laptop. So this is, this is also a very small. And anyway, just wanted to introduce it. I'm going to move on and do more. Let's go back to the slides. That's the code I'm using. I'm going to skip this thing about equilibrium, bus mileage, and demand for engine. We're going to talk more about equilibrium in just a second, but it actually builds on this idea. You develop from the model, give you the choice probabilities, and together with the state transition, you put these two things together. You essentially get a state transition for the state variables. Okay? Just like you also talked about, right? Once you put in your sigma there into the p's, and you get the transition matrix from state today to state tomorrow. You can find the ergodic distribution of that, the equilibrium distribution. Then you get the equilibrium distribution of mileage. From that, you can calculate and aggregate to demand and change those parameters to get the demand curve. That's the last part of John's paper. I'm going to skip that. Okay, which is what we have here. Okay. So why do I like this? I think parameters and models just much easier for me to understand as an economist. We're making lots of assumptions, right? But these are economic assumptions. I understand what it means to say, okay, the cost function depends on mileage in this and this way. It may be a restricted model. You have good ideas to what should else be in that cost function. But then let's talk about an extended model. Compared to some like statistical unconfoundedness assumptions, I think that's very personal. It's harder for me to understand. Okay, then you can do counterfactuals, right? You change, if you were to believe that these parameters are policy invariant, you can make out sample predictions with this model. You can test theories against each other, and then I just think the models are more attractive. But we are imposing more structure and making more assumptions. At least I think we were being very explicit about them, but computational complexity may actually force us to reduce the number of state variables. That's not so, but that's where the neural nets comes in and helps us. There's cursor originality, identification problems. Okay, let's not talk more about that and move on to MPAT. Constraint optimization approaches to structural estimation. I still have like half an hour or something, right? Okay. This is some serious gourmet shit. I would have been happy with some taster's choice. Oh, it's pretty good.
No, but I mean, like, 40 minutes ago, and still not cold.
No, it's pretty good. It's pretty good. Okay, let's talk about impact. Okay, so the overall idea with impact is instead of repeatedly solving these fixed points as you search over the parameter space, you just need to make sure that the Bellman equation holds at the maximum of the likelihood function. That the equilibrium constraints, the Bellman equation is an equilibrium constraint. That holds. And it doesn't hold, it's not only used in the context of single agent dynamic discrete choice models like the Gaussian replacement problem. It's also used for random coefficient, Loci demand models, where there's also a fixed point equation. Those of you who knows BOP. Or discrete choice games of incomplete information. There is more equilibrium constraints there, right? Because there's more players, so everybody has a Bellman equation. They all need to hold and need to have mutually best responses. And so this approach of imposing these constraints is a general. I'm going to just focus on Sue and Judd, who introduced it and made a house race with NFXP and the house cycle problem. Okay, this is what we just saw, okay? Unconstrained problem, maximize likelihood function with respect to the parameters only, but then changing the expected value function choice probabilities on the run every time you evaluate the likelihood. You could also follow it as a constraint optimization problem like this, but now there'll be more variables. They're going to be the structure parameters theta, but there's also going to be the expected value functions, more choice probabilities or integrated value functions, however you represent that equilibrium constraint. So you can maximize this likelihood, but then instead of, I mean, once you know what the expected value and the parameters are, you know everything that goes into the logit formula and likelihood function. Of course, it can't be anything. It has to be the stuff from the model, and then what you do is you impose it as a constraint that the Bellman equation needs to hold.
What does MPEG stand for?
One more time.
What does MPEG stand for?
Mathematical programming with equilibrium constraints, MPEG. So about that. So Sturctual, they did two implementations. They did one in a programming language called AMPL. It's a high-level programming language where you essentially just specify the equations, and then there is some state-of-the-art solvers beneath that high-level programming language. Very intuitive and easy to write. Like those of you who've done macro models, you probably know GAMS if you've not used AMP. It's similar to that. And then it calls solvers, constraint optimization solvers, for example, from Nitro or Conopt or SNOpt or whatever they. The cool thing about this is research has to do with it, not so much. It does automatic differentiation for you. So you just specify what the likelihood function and the Bellman equation is. You don't have to think about computing derivatives of the likelihood function, derivatives of constraints. All that stuff is done for you by automatic differentiation. I would say if you do it in Python today using JAX, you probably get automatic differentiation as well, right? So things are changing. And I think they made a very good point that, you know, we're economists, even though I like to, you know, code out my own constraint optimization problem, to solve a problem, other people should do it, okay? So that's a real benefit of that implementation. It also, yeah? You have to pay for Nitro, yeah. At the time in MATLAB, there was something called fmin_con. It was terrible. Nitro was just much better. It's not that bad anymore. That I don't know. Can you answer that, Friedrich? I'm not sure. The bottom line is not so much Nitro, more that there's someone else who wrote the constraint optimization problems doing all this stuff for us. Then they're comparing with the MATLAB implementation here, where the user needs to supply the Jacobian of the constraint. That's a derivative of the Bellman equation. And the second order derivatives, the likelihood function and the sparsity patterns by hand, and you can do that. In their implementation, they were not supplying second order, this is a typo, second order analytical derivatives. They have the first order derivatives. And then you can use Nitro using something called KGR. Okay, now, one of the things they emphasize is the use of sparsity. And that's a key factor for implementation. That's sparsity, using the sparsity patterns, and then also analytical derivatives. If you look at the Jacobian of the constraints that's EV equal to gamma of EV, right? There's, say we have 175 grid points, there's 175 constraints and 175 EV variables and 5 parameters, structural parameters, 180 parameters. Okay, and yeah, bigger model, it's a bigger Jacobian. So down here, you got all your constraints and you got all the parameters here. And if it's 0, then it's white. If it's not 0, then it's blue. So you clearly see it's sparse. Okay, so no need to numerically calculate 0 if you know it's 0 already. Okay. And even better, if you can calculate this analytically, your JAX could do it, then things are going faster. You don't have to value the Bellman equation 108 times to go to get all those derivatives. I'm not going to talk about Hessian, but it's also sparse. Okay, where's the sparsity coming from? Well, at least for the last part over here, which is derivative with respect to changes in expected values, where each point corresponds to a point in the state space, well, that sparsity is just coming from the sparsity of the state transition, right? The fact that you're not driving 400,000 miles a month and you're not driving backwards. And then essentially those derivatives here, you can show it's really just the choice probability weighted sums of those state state transition matrices. Okay? With some probability, you don't replace, and then you take that, and then some plus 1 minus that probability, or the probability that you do replace, and multiply with the state transition for replacement, and you get something that looks like this.
Are the axes on these miles? Not on this one, on the next slide.
If there's any x's,
The x and y axes, the units.
these here, this is the miles today. This is the miles tomorrow. In fact, it's just the index number of the grid point. Miles go from 0 to 400,000. Okay, but this goes from grid point 0 to grid point 175. Okay, let's do some Monte Carlo. And what they do is essentially they take that table I showed you before from John's paper, table 10 with 175 grid points, take those parameters, simulate some data sets, and see if they can estimate back those structural parameters using Monte Carlo. Okay, so the parameters, this should be a comma. Otherwise, I think most of it is, this should also be a comma, sorry about that. I'm keeping correcting that typo, and then you get some more version of the slides. I don't know what's happening to me. Anyway, then they make the comparison, and what they look at is the number of times it converged out of 1,250 runs. Now they're doing 250 Monte Carlos, but then they do multi-starts. So they start the parameters at 5 different places, okay? And you see, most of the time, MPEG ample is actually working pretty well. The MPEG MATLAB, sometimes it's even better in terms of the robustness, but it's slower, okay? 0.1 second. Versus 8 seconds. And then they compare with NFXP, which is what I just did. And it says, okay, now if we increase the beta here, we go to something like 2 minutes to estimate the replacement.
Can I be a bit annoying?
But
So like this, this time measurement, I think it's absolutely meaningless.
okay.
No, I mean,
Well, let's count something else. Let's count something else. This is
I don't have to be annoying here, but I'm just saying like this is heavily depends on the implementation.
of course it does. Okay.
And this is the average, right?
This is the average across many runs, and I know that this is ample, this is MATLAB, and who wrote the code and all that. But we can count something here. The number of times you evaluate the Bellman operator. That's not something that's
No, exactly.
depends on software, which is why we have it here. 748,000 evaluations of the Bellman operator on average to do NFXP. And then I saw this number, I thought, holy cow, how could John do that in 1987? Okay. So let's see if there's something we can do about that. Okay, because as you're right, implementation matters. Okay, first thing is read your manual. Okay, because John actually made a nice manual, described in detail what he did, and so we just try to replicate that. Turns out that there are some things that are important for that implementation, like the way you calculate log sums and logit formulas. You need to use not success approximations, but Howard's method or Newton's method. You need to provide analytical gradients of the Bellman operator for NFXP. You need to provide analytical gradients of likelihood, and then use what John suggested at the time, the BHHH algorithm that uses the information identity to make the approximation of the Hessian using only first order derivatives. So I'm just going to go through this step by step. And so in some sense, this is not so much a talk about NPEC. It's more about how to do NFXP correctly. Okay, so here are the links. I only had access to version 6, but I know there's one from 1985. It's virtually the documentation manual. I think it's online. Okay, so what does that manual says? This is the first step in the survival kit. It says documentation manual version 6. Formally, one can view the nested fixed point algorithm as solving the following constraint optimization problem. But that's NPEC. Okay, that was in the manual. Okay, so I guess this idea is not that's not what's new. It's the implementation. Then you also find something else that gives you a very nice description of a nested fixed point algorithm. Okay, you start here with some starting values of the expected value. Okay, and then you initialize the expected value with those values. You do a contraction iteration. You do a number of contraction iterations, and then if you're sufficiently close, if it converged, well, then you can calculate the derivative of the Bellman operator. And then you do Newton, and for that you need the derivative of the Bellman operator. And then you check, okay, are we close to tolerance? Then you afterwards you compute the derivatives of the fixed point, not the Bellman operator, based on the byproduct of that algorithm, the derivative of the Bellman operator, and then you go to estimation. He explained this in detail how to do that. We're just going to replicate that. Okay. That's what the code is doing. Just that picture, and it's actually pretty nice. You know, folded a couple of times, put in the genes. You always have this manual on. Okay, very. So here are the choice probability, those choice probabilities. See, the problem is, especially when beta becomes very close to 1, these are infinite sums that are discounted. Not a lot of betas equal to 1, right? They're close to 1. So these numbers grow, it becomes big. What happens when you put that into an exponential? Big divided by sum of bigs. Okay, that's just giving you numerical overflow. Be careful when you do logit formulas, right? So that's a good old trick. You can just make that little adjustment, right? You just subtract the value, you get exactly the same. What's a good value to subtract could, for example, be the maximum across all the decisions. Then you're sure that you have something at least maximum 0 in here. Then maybe you get overflow in the worst case, right? But down here, you would always have something that's possible, for example, the exponential of 0. And so you get a nice things that are bounded between 0 and 1, and you kind of avoid those annoying overflow and the problems. Same thing with the log sum, which is the sum of those exponentials. You can just take that outside. You avoid those taking exponentials of very big values and summing them together. So that's good to keep in mind. Okay, now you're going to use not only successive approximations, but also Howard's or Newton. And we already seen that the line for a successive approximation was way above the line for Howard. So what John proposed was to start with successive approximation to actually get into a domain of attraction, and then at some point switch to Newton, because what you get with Newton is you get quadratic convergence, which means that as you get closer and closer, the error bound is just going from something like 10 to the power minus 2 to 10 to the power minus 4, 8, and 16. That's quadratic convergence. That's what Newton promises. So if we can use successive approximations first and then go Newton, then that's pretty good. I'm going to show you actually some sort of heuristic for making that choice. Anyway, here's how you do the successive approximations. Let's try to do it here on my computer. It's called Run FXP. FXP. Okay, And let's just look at the code. Run FXP. Change a few things. Okay, so what I'm going to do is I'm going to just switch off this poly algorithm, just do successive approximations, allow it to do like enough iterations. So they say, let's just say 5,000, maybe 50,000. That should be enough, right? To solve this model. Run FXP. What did I do?
One comment at line 7.
Line 7, I made a bug. Oh, sorry. I'm in transition. Sorry about that. Okay, so it goes on. And so here's a tolerance. That's its number. What should that be? I want it to be some close to machine precision. It's still 0.01, right? So we're not quite there. We did 50,000. Oh, it's over here. But we could do more, like 500,000. Okay, take some time. Okay, yeah, we'll get there. You see, it does eventually get to 0, right? But it's pretty slow. What you do, let's just stop it and look at the results here after 500. What you see here is this is the maximum absolute difference of two successive approximated value functions. This is a relative difference if you compare, if you divide them with each other. What is this number? Well, those of you who knows what beta is, recognize it. 0.999, that's a discount factor. This is not a coincidence. Let's go back and see. Okay. Here, so here's just collect the data. Collect the data, look at the error bounds. This is what we get with successive approximations. Here's the iteration count down to 10,000. And here's the error bound. You see it slows down as beta becomes closer and closer to 1. Here you got 0.999. Here you got a lot of discounting, so 0.95. Okay, so here's convergence. If you take the log of that error bound, now you see why we call it linear convergence. And in fact, the slope of this line is 1 minus beta, beta minus 1. So this is not so surprising, right? Trying to solve an infinite horizon model by a finite horizon approximation, and if you care a lot about the future, it's not so I mean, it's not so surprising that you need your approximation with many periods needs to include many periods, right? Do many iterations. Now with Newton-Kotorovich, well, what you see is after a couple of iterations, we are close to those relative values of the expected values are close to that beta. If you then switch to Newton-Kotorovich, then you see, okay, 0.1 intolerance, 0.4, 0. So it's like the digit is to the 10 to the power minus 2, minus 4, minus, well, here it's 6, and then essentially it's to the power minus 2. So you got something that looks like quadratic convergence. It's like the exponent is jumping all the time. You can plot that here, it looks like a quadratic. And that works even though beta could be very close to 1. So that does not rely on the contraction mapping problem. Okay, so when do you want to switch to Newton? Well, let's suppose, here's a little example. Suppose that you already got the value function, the expected value function. The true one is EV0. And then we just add a little constant. Now, when you do successive approximations of that, it's going to take some time before, I mean, if you have 0.999 beta, it's going to take those 100,000 iterations before it can remove it, because it just eats a little fraction of it at every iteration. But let's calculate those tolerances. Okay, so you start with EV0. This is our starting value. It's a true function plus a constant. We substitute in, okay, and then now essentially this is once you put this into the Bellman range, it's EV plus beta times the constant, right? Just moved out with beta in front. You do another iteration and you get, here you got 1 minus beta times beta. Now you get beta times 1 minus beta. You take those two tolerances, divide with each other, that's exactly where you get beta. So that's how our kind of sign, only the level of the expected value functions are left, or at least if only the level is wrong, then you have that relative tolerance being close to beta.
Are we defining lambda, not lambda, that's a delta. Delta EV0 equals EV1.
I'm not sure, where's the delta?
No, sorry, not delta, gamma.
Gamma.
Yeah.
Gamma, that's a Bellman operator.
Yeah, I'm saying that's, are we defining it so EV1 equals gamma of EV0?
You're defining it so that gamma, if you put that a constant into that Bellman
Maybe
operator.
even before that, just on the previous.
Yeah.
Yeah.
This is just measuring the error bound between our initial guess and
But I'm saying like EV1 is EV1 where you pass EV0 through the gamma operator?
Oh, yeah. Okay, yeah. That's after another iteration. Okay, now the thing here is Newton, if there was just a constant left, right? You take derivatives, it's gone. Okay, so it's immediately you strip away that little constant. So this suggests that we should switch to Newton whenever relative tolerances are close enough to beta. That's the point I want to make. And so that was what we were doing right here. Okay. And you can also do that in the code, of course, right? So we just turn this algorithm poly back on. That's doing first successive approximations. And then whenever relative tolerances are close to beta, it jumps to the other one. And so we can try to run that. And you see here, as you get close enough to that, you start to see this quadratic convergence. Okay, it jumps to Newton. Okay, let's move on. Okay, so you need to use this fixed point algorithm. This is just a summary of what we just done. Then you need to calculate analytical derivatives in order to calculate those that make that Newton step, right? You need the derivative of the Bellman algorithm. Well, it's not that hard to compute that derivative. It's essentially this choice probability weighted sum of conditional state transition matrices, those pies I showed you before. Just weighted with the choice probabilities and then multiplied by beta. That's what the derivative of the Bellman operator is. This vectorized. This is just one line of code in there. So it's not so hard. Here's the code. Let's move on. Here's another implementation. This is for the Bellman equation in integrated value function space. This is the expected value. Okay, so you start calculating the choice specific values of keeping and replacing. Okay, then you resample that log sum like we talked about, right? Take out the max, ensure numerical stability of the log sum. And then if you want to have the choice probabilities, return that, making sure that it's numerically stable. And then if you ask for it, well, you also calculate the Bellman, the derivative of the Bellman. Okay, now we have the derivative of the Bellman operator. We also want to have analytical gradients of the likelihood. And what is that? Well, that's just the gradients. That's similar just to a standard conditional logit model. Okay? It's just that the derivative of the utility is now the derivative of the choice-specific value functions. Okay? You estimate conditional logit models where it's like x beta in there, and then derivatives with respect to a change of parameters is just going to be x, and then you would have something like, the residual from the model had to be uncorrelated with explanatory variables. Okay, so, but here it's different. It's the value function. How do you calculate that? Well, you take the derivative of these choice-specific value functions. This first part, the derivative utility, we can calculate that. We have a parametric form, right? Easy to differentiate. But then we need to have the derivative of this second part that includes derivative of the integrated value function, or this fixed point. How do you compute those? Well, you need to use implicit function theory. Okay. Here, the derivatives, well, it depends on the derivative of the Bellman array. What we just got those from Newton-Kotorovich, so we don't have to compute them again. We just reuse this, and then we can calculate essentially everything we need. So we can do maximum likelihood analytical gradients using a dynamic structural model. Okay, you can put all this together. It's actually smaller in MATLAB than in Greek letters. So, last thing, I think I have 2 minutes left to talk about the last step. It's a Bertel and Hausman maximization algorithm. You know Newton-Raphson, right? How to maximize functions using this iterative approach, where you use the gradients and scores, some of the scores, right? And then you need the multiply with the inverse of the Hessian. Do a quadratic approximation and put derivatives to 0, and then take the step that maximizes that quadratic approximation. Okay, now those Hessians, they require differentiating twice, right? So why don't we just, instead of using those Hessians, use what Bertel and Hausman suggests, use the outer product of the scores motivated by the information identity. Since we're doing maximum likelihood, right? We can do that. So we just replace those by an approximation to the Hessian, namely the outer product of the scores. It's valid because of the information identity. So use the structure of the problem you're trying to solve. So why is this a good idea? Well, if you have a non-concave part of the likelihood function, okay, like a convex area, what is pure Newton-Raphson going to do? Well, in this area, it moves in the opposite direction of the gradient because the Hessian is negative symmetry. Okay, it's not positive definite. You should, like, oh, I was reversing something. Sorry about that. There's minus in front. Okay? But this guy here is always ensured to be positive definite, right? It's the outer product of the gradient is like the score squared, right? Something squared is always positive. So if you were using B=H in this area, you would always still move in the direction of the top. Okay? You may overshoot, but then you can do a step halving or something, or a line search. And it's very easy to implement. Okay, so it has these advantages. Our program score is always positive definite, and it's always going uphill for small enough lambda. And it does not rely on second order derivatives. Okay, and of course, information density needs to hold, so it's only crude approximation of true parameters for large number of observations, for well-specified models, so on. I think it works pretty well. We're going to use it in the next lecture to estimate a model with like 150 parameters. Okay, so this is what the president, the former president would have said. Okay, the way to the top is use B=H. I'm not trusting him in every aspect of life, but this is true. So convergence achieved. And then what we did is we redid the whole thing, compare the NFXP to MPAC. And so here are the numbers, the computer time, the number of times it converged for those 1250 Monte Carlos is 1250 for NFXP. We actually also improved a little bit on the MPAC by doing these adjustments to the log sums and so on. And look at the computer time, it's virtually the same. If you increase the sample size, it's actually much faster to do than nested fixed point. So I'm going to conclude with this. just say, maybe Sue and Judd actually didn't do the most efficient implementation of the nested fixed point algorithm. I mean, this is not to bash MPEG because it's still working pretty good. Okay, it's just not as better in orders of magnitude. If you use NFXP as was originally proposed, they're equal in performance. It does not slow down as beta goes to 1 because we're using Howard or the Newton algorithm. Some desirable features of MPEG is it's very easy to do the ample or the high level implementation, and it can easily be, and you would not have to bother computing all those derivatives by hand. But I think today we could do that in JAX, right? Or they are not that hard to actually implement. In terms of inference, calculating standard errors is completely trivial because you just take the, the diagonal elements of this, or the inverse of the Hessian, just as you would normally do. But for MPEG, the standard errors would need to have some additional adjustment because it's not the Hessian is not taking into account the parameters of the expected value function is changing with the change of those parameters. You need to use the border Hessian and use appropriate formulas. Just a little bit more complicated, but actually Gregor Reich is like a former SAIS alumni, and Ken Judd has a very nice paper where they show how to do it. So it's just a little bit more complicated, but yeah, so that's kind of some of the pros and cons. Let's take a 10 minutes break.